Hi everyone, my name is Rahal and I'll be presenting to you our work on haptic shear control methods for robotic cutting. Starting with the motivation behind our work. Robotic cutting is a relevant task in different applications, for example surgical robotics, manufacturing, and waste management. It is particularly interesting for shear control because it requires high dexterity and can have serious implications if it fails. In addition, cutting applications have a variety of constraints that need to be taken care of. For example, no lateral motion and no rotation in place should be done, not to ruin the material that is being cut or the scalpel itself. And several shear control architectures have been presented to deal with this issue. For example, in the work of Wazar et al., the authors introduced non-holonomic constraints in a cutting task. The task consisted of cutting a straight line and insulating foam, and the authors compare four different control modes. The main limitations of this work are, however, that no constraints are propagated on the master interface, and the task considered is fairly simple, so they only consider a simple straight line. They also mainly focus in their work on time delays, which are not present in our system. In this work, we present the master and remote robot coupling in the teleoperation scenario shown in the figure. We also present three different control modes, and we compare them in an in-depth user study which studies the different parameters involved. The three presented methods are the following. We have the standard haptic teleoperation T, we have the unicycle approach U, and the car-like approach C, and I will be giving more details on these methods later on. In all the three modes, the master and the remote robot are only allowed to rotate around the z-axis. However, the three translation directions are left free. And the user receives two types of haptic feedback. There are the contact forces, which are reflected from the environment, and the non-holonomic constraints. Starting with the teleoperation mode, in this mode, the user has full control of the three planar degrees of freedom and on the vertical direction, and the remaining degrees of freedom are blocked. So as you can see in the video, in this mode, the user can move freely in the plane, he can move laterally, can also rotate around the z-axis, and can move vertically along the z direction. In order to take into account the cutting task, we also present a unicycle mode where the lateral motion is blocked, and this constraint is applied both on the master side and on the remote robot side. So the scalpel is constrained to only move along two translation directions, the cutting direction and the vertical direction. So you can see in the video that the user can only rotate and move along the cutting direction. The user can also move vertically, however, the lateral motion is blocked, and this constraint rotates as the master device also rotates. Finally, we present a third mode, which is the car-like approach. In this method, we also add another constraint, which is that the slave robot should not rotate except if there's also a translational direction commanded from the master interface. So as you can see, in this case, we have a soft spring which is added also on the master side in order to show the user what is the current orientation of the slave robot. So in the video, you can see that the user can move, in this case, forward and backwards, and there is a soft spring which shows the user the current orientation of the robot. The user can also move along the cutting direction but not perform any lateral motion, just like in the unicycle mode. Finally, we performed experiments with 12 participants in order to compare the three shear control methods. The three conditions were tested over three different trajectories. One of them is a straight line, the second is a bent line, and the third trajectory is a sinusoidal shape. And the results have shown that, compared to teleoperation, both the unicycle and the car-like approach perform better in terms of the metrics presented, especially in terms of the lateral forces. And then when we compare the unicycle approach with the car-like approach performs better. However, when we asked the users to rate the different methods, most of them preferred the condition of the unicycle, and only one participant preferred the car-like approach. And this shows that even though the car-like approach performs better in terms of objective metrics, it is not always preferred by the user because it is a bit more complicated. So as a conclusion, we presented in this work three different control methods for assist cutting. We imposed non-holonomic constraints on the master and on the remote robot, and we compared the three control modes in a user study, which shows that both the unicycle and the car-like approach outperform simple teleoperation in the objective metrics. It also showed the difference between the objective and the subjective metrics, and that the high effective control modes are also highly demanding and are not necessarily preferred by the users. Thank you.